Imagine two activated carbon in front of you. Carbon A has a specific surface area of around 1500 square meter per gram, and carbon B has almost 3000 square meter per gram. So which one looks better? And most of us will choose carbon B, almost double the surface area. So we expect much higher charge storage. But here is the surprise. Inside a real supercapacitor, carbon B can still not perform good. A carbon with lower BET surface area can give better capacitance, better rate performance, and better practical performance. So something important is missing from that 3000 number, and that is exactly what we are going to find in this video. Because the real point is not how much surface does the carbon have. The real point is how much of that surface can the electrolyte actually reach and use. And this small difference changes the whole picture. In the previous video, we understood why activated carbon remains so important in practical supercapacitors. And today, we are going inside those carbon pores. We will see why some surface restores charge effectively, while some surface contributes very little. Now, let us begin with the number at the center of this story, BET surface area. In porous carbon research, surface area gets a lot of attention. 1000 square meter per gram, 2000, 2001, 2002, and sometimes even higher, that is 3000. And the logic looks perfect. An electric double layer capacitor stores charge at the electrode electrolyte interface. So more surface means more interface, and more interface should mean more charge storage. Simple but not complete, because four other factors now enter the story. Accessible surface area, poorly accessible or dead pores, poor connectivity, and electrode density. Now notice one important point. A large surface can exist deep inside the carbon. But if electrolyte ions cannot reach that surface, it cannot contribute effectively. And there is another step also. Reaching the surface is not enough. The ions must reach it fast enough during charging and discharging. So we actually have two different ideas. One is the surface area measured during the characterization. The other is the surface that participate during electrochemical operation. And the gap between these two is the surface area trap. A value of 3000 square meter per gram can look excellent in a table, but the supercapacitor does not read that table. It responds only to the surface that ions can actually use. Now the obvious thing to understand is this: what exactly does the BET measure? The BET surface area is commonly measured using the gas adsorption. Nitrogen gas is often used as a probe. The gas enters the porous structure and interacts with the internal surface. And from this adsorption behavior, we estimate the surface area. And this gives us very useful information about the porous structure. But now switch from the instrument to the actual supercapacitor. Inside the device, nitrogen gas is not storing charge, and the major contributor are the electrolyte ions. And these ions behave differently. An electrolyte ion is often surrounded by solvent molecules, and this surrounding layer is called solvation cell. And in simple words, the ion is moving with solvent molecules around it, so its effective size becomes different from its bare size. Now compare both the situation. During BET measurement, gas molecules probe the pores, and during supercapacitor operation, electrolyte ions have to enter those pores. Same carbon, different probe, and different conditions. This difference matters. So remember this simple distinction. BET tells us how much surface is measured, and electrochemistry tells us how much surface is actually working. The two are connected, but they are not the same. That is why highest BET value does not automatically give the highest capacitance. And now we can divide the internal surface into two useful ideas. accessible surface and poorly accessible surface. Think of the carbon as a huge internal network. It contains thousands of pores, and some pores are easy to reach. Electrolyte ions enter them and reach the carbon surface. These regions contribute effectively to the charge storage. This is the accessible surface, but other pores are more difficult to use. Some have narrow entrances, some are poorly connected, some lie behind the slow transport pathways. So the surface exists physically, but the electrochemically its contribution becomes small or negligible. This is the key point. Surface that exists is not automatically surface that works. So whenever you see a huge BT value, go one step deeper. Do not look at only do not look only at how much surface is present. Look at how much surface is actually working. And what decides whether ions can use that surface? One major factor is pore size. The activated carbon contains pores of different sizes. We commonly discuss micropore, mesopore, and macropores. Each has a different role in the pore network. Macropore help electrolyte enter the large structure, and mesopores help connect different pore regions. And micropore provides a large internal surface and often contribute strongly to the charge storage. But here comes an important twist. Not every micropore works equally well. A pore can have useful internal surface, but if its entrance is restricted, the ions struggle to use it. A pore can also be poorly connected to the rest of the network, and that reduces its contribution. At the same time, very small pores are not automatically bad. This is where the behavior becomes especially interesting. Remember the solvation cell. An ion is surrounded by solvent molecules. When that ion approaches a very narrow pore, it can lose part of this surrounding solvent. This is called partial desolvation. And in simple terms, the ion becomes effectively smaller. It can then enter a pore that initially looked too narrow. So a very small pores can still contribute strongly to the charge storage. And this gives us an important rule. It is not bigger pores are always better. And it is not. Smaller pores are always better. The real idea is the pore and electrolyte must match. Ion size matters, solvation matters, pore entrances matters, and the transport pathway matters. Now see what happens if we keep the carbon exactly the same but change the electrolyte. BT surface area remains the same. The pore structure remains the same, but the ions change, the solvent change, and the solvation behavior also changes. The performance can change. Same carbon, same BET area, different electrolyte and different result. So pore size cannot be discussed properly without considering the electrolyte. But even a pore with perfect size is useless if there is no good route to reach it. That brings us to pore connectivity. Suppose we have created pores with excellent dimensions. Is that enough? Obviously no. The pores must also be connected. Follow one electrolyte ion. It starts in the bulk electrolyte. Then it enters the electrode. It moves through the larger pores. Then it travels deeper into smaller pores. Finally, it reaches the internal carbon surface. Now put one narrow or difficult region somewhere in this pathway. What happens? Everything beyond that region becomes harder to reach. This is why porous carbon should not be looked as a collection of separate holes. It is better to think of it as a connected transport network. And in this network, a pore is useful only when the ions have a good route to reach it. A carbon can therefore have a huge internal surface area, but poor connectivity can hide much of that surface from effective electrochemical use. And this is another place where a huge BET number loses its advantage, and the effect becomes even stronger during fast charging. At slow rates, ions have more time to travel deeper. At higher rates, time becomes limited. Poor pathways then become a serious problem. But connectivity is still not the full story. Even a perfectly connected pore network cannot work properly if the electrolyte ion not enter it well. Now we can reach another important factor, that is wetting. Wetting sounds simple, but it has a major effect on porous electrodes. Wetting means how well the electrolyte spreads over the electrode and enters the internal pore network. For charge storage, electrolyte ions must contact the carbon surface. Poor contact means poor electrochemical use. Now here is the important point. Wetting does not depend only on the carbon, it depends on the electrode and electrolyte together. The solvent matters, surface chemistry matters, ion type matters, ion size and solvation matters. It depends on the electrode and electrolyte together. The solvent, surface chemistry, ion type, ion size and solvation, all sorts of things are matter. So useful surface area is not only a property of the carbon, it is the property of electrode electrolyte pair. This has a very important consequence. Take exactly the same carbon, same BET area, same pore size distribution, same electrode material. Now change the electrolyte. Performance can change. Why? Because wetting changes, ion transport changes, effective ion size changes, and access to the narrow pores changes. Nothing happened to the BET number, but the device result changed. This is why comparing two materials tested in very different electrolytes needs care. Now we have discussed surface accessibility, pore size, connectivity and wetting. But a real device introduces another important limitation, that is space. And that takes us the electrode density. Now imagine a carbon with an enormous BET surface area. It looks excellent during characterization, but the powder is extremely light and fluffy. A small mass occupies a large volume. Is that a problem? For a real device, definitely yes. A supercapacitor has limited space. We cannot keep increasing electrode volume. So performance per gram is very important. But performance per unit volume is also very important. And this is where the volumetric capacitance enters the picture. Gravimetric capacitance tells us the capacitance related to the mass. Volumetric capacitance tells us the capacitance related to the volume. And now, here comes another surprise. A fluffy material can show excellent capacitance per gram, but if its packing density is very low, its capacitance per volume can be much less attractive. So a denser carbon with a lower BET surface area can become much more useful in the practical device. Again, the winner changes when we change the way we look at the material. This gives us a design balance. We need enough power for ion movement. We need enough internal surface for charge storage. But we also need enough active material inside the available device volume. So high porosity alone is not enough. High density alone is also not enough. The electrode needs the right balance. Whenever you see an extremely high BET value, check a few more things: mass loading, electrode thickness, packing density, and volumetric capacitance. And without these values, the practical picture remains incomplete. Now, there is one more powerful way to test whether that huge surface area is truly useful or not. Ask the electrode to work faster. Suppose an electrode gives excellent capacitance at a slow rate. Very good results. But slow operation gives ions plenty of times. They can enter the electrode, move through larger pathways, travel deeper, and eventually reach difficult pores. Now increase the current or increase the scan rate. The available time becomes much shorter. And now the pore network has nowhere to hide. Its transport limitation becomes visible. If the network is well connected, ions still reach a large part of the surface. If transport is poor, capacitance falls quickly. So high rate performance tells us something that BET cannot. It tells us whether the surface stays useful when the device is asked to work fast. Two terms help us to understand this: tortuosity and bottlenecks. Tortuosity means the ion's pathway is long and indirect. Think of two roads. One is straight, the other reaches the same place through many turns. The second route takes longer. A bottleneck is narrow region that restricts ion movement. Now imagine a huge surface area sitting after that bottleneck. The surface also exists, but during fast charging, ions struggle to reach it. So its contribution falls. This explains why a high area carbon can perform well at low current density or low current and lose a large part of its capacitance at high current. For a supercapacitor, this matters a lot. Fast charging and high power are key advantages of these devices. So surface that works only during very slow operation is not equally useful for high power performance. This gives us a stronger definition. Useful surface area is the surface that remains accessible at the operating rate of the device. Now let us make this practical. Suppose you open a research paper tomorrow. Okay, the authors report a new porous carbon with a huge BT surface area. What should you check next? First, look at the BT surface area. It is useful information. But do not stop there. Next, check the pore size distribution. Look at the micropores, mesopores, and macropores. Then check the electrolyte, which ions are present, which solvent is used, and how well do the ion dimensions match the pore structure. Then check what is the mass loading. A very small amount of the active material can give a very different picture from the practical electrode. Now check the electrode density. At low density electrode can look excellent per gram but weaker per unit volume. Then look for two electrode device data. This becomes especially important when the practical performance is being discussed. Check the capacitance, check the energy, power, and cycling stability. After that, check the rate capability. Does the electrode retain its performance when current increases, or does the capacitance falls quickly? That tells us about ion transport. And finally, check the EIS. EIS means electrochemical impedance spectroscopy. In simple terms, it helps us to understand resistance and ion transport behavior over different frequencies. Now let us return to where we started. Carbon A had around 1500 meter square per gram. Carbon B had almost 3000 meter square per gram. At the beginning, carbon B looked like the obvious winner. Now we know that the answer depends on much more. First comes accessibility. Can the electrolyte actually reach the internal surface? Then comes pore size. Do the pore dimensions work well with the ion and its solvation behavior? Then comes connectivity. Can ions reach those pores through an effective pathway? Then comes wetting. Does the electrolyte properly contact the internal surface? Then comes electrode density. Can enough active material fit inside the available device volume? And finally comes rate performance. Does that surface remain accessible when the charging and discharging becomes fast? So next time you see a huge BT surface area in a paper, do not let that number decide the results for you. Look deeper. Check the pore size distribution, electrolyte, mass loading, electrode density, rate capability, also impedance. More importantly, the two electrode device performance. And that is where the real performance is rewarded.